One famous thing from math that involves complex numbers is this image, which is called the Mandelbrot set, and maybe you've seen this picture before. Now you're ready to understand what this picture is and why it looks like that. Why are some spots black and some spots are green and some are purple? And that's what this lesson's about. So here is a recursive function, and recursive function tells you what the first number is. In this case, 2 is like the first number of like a sequence, and it tells you how to calculate out other numbers. For instance, to calculate out x1, we could use the second half of this recursive formula. x1 is x0 squared plus x0, which in this case is 2 squared plus 2, which is 6, so 6 is the second number. To get x2, you do x1 squared plus x0. See, the x0 is part of that. That's always x0. So in this case, x1 we just calculated to be 6, so it's 6 squared plus 2, which is 38. And x3 would be x2 squared plus x0, which is 38 squared plus 2, which is 1446. And as we can see, this is going to get really, really large. So if I use 2 as my x0 value, it gets really large. And if I use a number bigger than 2, it's going to get even larger. But if I use something less than 2, for instance, what if I make 0 the first number? Well, in that case, it's going to be 0. Then x1 is going to be 0 squared plus 0, which is still 0. And x2 is going to be, again, 0 squared plus 0, which is still 0. Well, that one doesn't get very large. If I pick some kind of decimal number as my starting value, let's say I say 0.5. We're going to use the same recursive part. Well, I'll tell you that when you use 0.5 as your starting value, it actually does increase 0.75, 1.06, 1.6, and then it gets up to 3, and it's eventually going to get really large also. So 0 is one that does not get very large, but 2 and 0.5 are both things that will get really large. So you might wonder, how close to 0 can I be where it will get, like if I make it 0.1, is that going to also get really large? Well, actually, 0.1 will not get very large, and 0.2 is kind of the last positive number that stays kind of small. It creates the sequence 0.2, 0.24, 0.26, 0.27, and it pretty much stays at around 0.27 from then on. Now, negative numbers might do something like unusual. Like if I put x equals, for instance, -1, then x1 would be -1 squared, which is, I'll just go like this, -1 squared plus -1, which goes to 0. But then x2 would be 0 squared minus 1, which is -1. And x3 is back to -1 squared minus 1, which is back to 0. So that one's going to alternate. If instead I try something more negative, like -2, x1 will be -2 squared, which is 4, minus 2, which is 2. x2 is going to be x1 squared, which is 2 squared, which is 4. Actually, that stabilizes also. Okay, what I'm getting at so far is that certain numbers will like sort of not get very large depending on the starting point. So -1, -2, we saw 0, even 0.2. But most numbers, like 2, for instance, anything bigger than 0.2, 0.3, 0.4, here we saw 0.5, grows. -2 seems to stabilize, but I think -3 won't. Let's check it out. -3, x1 becomes 9 minus 3, which is 6. x2 is 36. Minus 3 is 33. And that's obviously going to get really, really big. Well, what does this all have to do with this picture, the so-called Mandelbrot set? Well, before we go over the color Mandelbrot set, let's look at the black and white Mandelbrot set. This weird-looking picture is actually on the complex plane. Real, imaginary. And this is around 1, -1. Not exactly sure how high and low these things are, but it's all in this kind of range where this entire picture is on the complex plane, real and imaginary part, and most points are white. Everything out here are all colored in white. But then there's a small little blob of points that are colored black. And what's the difference between points that are colored black and points that are colored white? Why are some points colored black and other points are colored white? For instance, 0 plus 0i is colored black. And maybe some point over here, I'll just call that 0.2 plus 0.1i. That's also colored black. But out here, some number like, 1.5 plus 1.3i, that one's colored white. And what is it that determines whether they're colored black or white? Well, that's going to go back to this recursive formula. I'll tell you that because, first I'm going to look at numbers that are on the real axis themselves. The reason that 1, on this number line, this point right here is around 0.2 plus 0i. And that's because when you plug 0.2 into that formula as the starting number, it does not get very large. And 0 also doesn't get very large, and -1 doesn't get very large, and -2 also doesn't get very large. And that's why, at least on the number line, on the real axis, those points are all colored black. But remember how 0.5 got really big? Well, that we're going to color the point at 0.5 with a different color. And 1 got really big, and 2 got really big, and -3 also got really big. So if we can only use real numbers as our starting point, everything between around -2 and 0.2 would be colored black, and everything bigger than 0.2 or less than -2 would be colored white. So let's see whether the point, so the starting numbers that don't turn into really large things when you would run them through that equation are said to be in the Mandelbrot set. So the Mandelbrot set is a set of numbers, which includes the number 0 and 0.2 and -1 and -2. Those are in, whereas numbers like 0.5 and 1 and -3 are not in. And if I color all the points on that represent these numbers on the complex plane, if I color them all black, and I color all the ones that are not in white, I get this unusual picture. So let's see if I take the same formula, xn is xn minus 1 squared plus x0, and I test a complex number like 0.4 plus 0.5i. And I want to know, is it in or out? Because if it's in, I'm going to color it black on the complex plane. If it's out, I'm going to color that point. Well, if you run this through the formula, 0.4 plus 0.5i squared plus 0.4 plus 0.5i, well, it would be kind of annoying to work this out, but you could do it by hand if you needed to, and you would get around 0.31 plus 0.9i. And then if you ran that through the formula again by doing 0.31 plus 0.9i squared plus, not plus this thing, but plus the original thing, 0.4 plus 0.5i, that would turn into about negative 0.3 plus 1.1i. And if you kept on going, eventually when you got to number 6, it would be negative 1.8 plus 2i. Now if you ever reach a time where one of these numbers is 2 or bigger, then we can stop the process and we can say it's not in. Officially, as long as when the absolute value gets bigger than 2, we can say it's not in, but if either of these numbers is bigger than 2, then its absolute value is going to be bigger than 2 also. So it turns out that 0.4 plus 0.5i is not in, and that is why on this picture here, it would be, somewhere over here, 0.4 plus 0.5i, it would be colored in white. Now, something about this picture is sometimes always called a fractal, because if you zoom in on a piece of it, it starts to look like itself, like the miniature version of itself. And sometimes if you go onto YouTube and type Mandelbrot set videos, you can watch like a flyover where it zooms in over and over. You could have 2 points that are very close together on the near the border here. If you pick 2 points really close together, one of them is going to be in the Mandelbrot set, and another number that's practically the same number won't be in. And that's related to a type of math called chaos, where 2 things that start off almost the same can have very different futures. Okay, another thing. What's this with all the colors? Well, what these colors are, basically instead of making the anyone who's not in the Mandelbrot set, instead of just making them white, the color is a coding for how many times did it take to use this formula to get sort of kicked out of the Mandelbrot set. So in this case, it took 6 iterations before the number got kind of big. So I would use color number 6, which it looks like in this one that maybe blue was the first color, because those guys all got kicked out on the first time, and this was the second color, and then third and fourth, fifth. So the 0.4 plus 0.5i is somewhere in that little yellow region. So a number like negative 3, it actually gets kicked out right away because its absolute value is already bigger than 2, and that's why those are colored blue in the color Mandelbrot set. So when you go on the internet and see zoomed in stuff, you'll see all the colors and how 2 things, numbers that are very, very close together, could have different colors. It's called the iteration number, which is how many times it takes to get sort of kicked out of the Mandelbrot set. I mentioned before 0.2 plus 0.1i. If you ran that through the formula, well, it's going to be in the Mandelbrot set, but how would you know if you were calculating out with like a spreadsheet or something, whether, when can you stop? When can you be sure? If you're running through the iterations, let's say you get to 50 steps and it still is in the Mandelbrot set, or it hasn't gotten bigger than 2, none of the pieces have. Well, as a rule of thumb, if it hasn't gotten booted out of the Mandelbrot set by the 50th step, then they just say, yes, it's going to stay in there. I mean, it is possible, I suppose, that something was going to get kicked out on the 51st step, but I guess mathematically speaking, it's almost impossible for that to happen. So questions that you could be asked are, is something in the Mandelbrot set or not? Numbers like 2 and 0.5 even are not, whereas numbers like 0 and 0.2 are. And for imaginary numbers here, -1 is in, -2 is in, but -3 is not in the Mandelbrot set. And then for imaginary numbers, I have a spreadsheet program that I made where you could type in a number and it goes through the iterations for you. But you could also do it on a calculator. And now you'll also know when you see this picture that the colors is when, instead of making everything that gets kicked out of the Mandelbrot set, instead of making them all white, it makes different colors depending on sort of how long did it hold on before it got kicked out of the Mandelbrot set. You can see in this region here there's a lot of different colors, and two numbers that are very close to each other can have different iteration numbers. Okay, that takes care of the Mandelbrot set.